This is Unit 2 for Measurement, Part 2 Notes. At the end of this lesson, you should be able to differentiate between different types of units, express and manipulate chemical quantities using dimensional analysis, understand and use the metric system, and as always, use tables and graphs to infer, predict, and conclude. So any measurement depends on the unit that serves as a reference standard. Anytime you report a number, you need to have a unit after that. Because if you just tell me a number, what are you talking about? For example, how much money does your friend owe you? If you say 10, 10 what? 10 pennies, 10 dimes, $10, $10 million? That's a big difference. So anytime you report a number, you must include a unit. In science, measurement uses metric units that are based on powers of 10. And the International System of Units, or SI unit, is used in a scientific setting to allow equal comparison throughout the world. So if you look to the right, we have SI base unit chart, where you have the quantity, the unit base, and then the symbol. Anytime you're measuring length, you need to report that in meters, noted by a little m, or an undercase m. Mass, the SI unit is kilogram, also known as kg. Temperature is reported in Kelvin, a capitalized K, or even degrees Celsius, but Kelvin is the SI unit. Time is in seconds, and then the amount of substance, or a mole, which we'll get to later this year, its unit or symbol is MOL. The three major types of measurements that we use in chemistry can be described by length, volume, and mass. Length describes a linear measure of distance or size, and its SI unit is a meter. We've already measured length by using centimeters within the process skills lab. Volume describes the space occupied by any sample of matter. The SI unit is liter, and we can derive volume from length. Hence, the volume is length times width times height. If we have length in meters, width in meters, and height in meters, we can get meters cubed. Anything cubed leads to volume, such as meters cubed or centimeters cubed. We can relate that to a volumetric unit. Mass is a measure of the amount of matter that an object contains, and its SI unit is a kilogram. So we used a scale earlier this week in the process skills lab. That's different than what is known as weight. Weight is a force that measures the pull on a given mass by gravity. Hence, you will have two different weights if you were on the Earth and the Moon, because the Earth has a stronger gravity than the Moon does. So we can convert between all the different measurements, such as meter, liters, and grams. Just to recap, meters is a unit of distance, liter is a unit of volume, gram is a unit of mass. And there's different prefixes that we were able to convert between. So we can convert, let's say, a gigameter all the way down to a nanometer. Well, conversions of the metric system depends on these factors. I guess this came out wrong, but the third number should actually be an exponent, so I just want to correct that before we get started. Giga has a factor of 10 to the 9th, mega has a factor of 10 to the 6th, kilo has a factor of 10 to the 3rd, hecto has a factor of 10 to the 2nd, and then the deca has a factor of 10 to the 1. Everything else on the bottom, 1, 2, 3, -6, -9, that's all correct. If you look down at the bottom real quick, pre-AP and Academy, you need to memorize this chart. You need to know that a gigameter is a factor of 10 to the 9th, all the way down to nano, which is a factor of 10 to the -9, and the symbols as well. You will not be given this chart on any exam or test or quiz, so you need to sit down and memorize it. An easier way of helping you just sit down and memorize everything in order, I have a saying where that great man, King Henry, danced merrily, lazily, and gracefully down center, main, under Narnia. So we had the GMK HD, meter, liter, gram, that is your baseline. The mlg is your baseline, down the DCMU. So the first letters all represent the order of the prefixes here, so that can relate to their symbol. And then you also need to memorize their factor. Just know that going from the base up, you have a 1, 2, 3, 6, 9, and going down to the bottom, it is also 1, 2, 3, 6, 9, except the negative exponents only relate to the fact that they are small numbers at the bottom, while they're large numbers at the top. I'm going to be working with this chart a lot, so you'll see this on future slides. But again, pre-AP and Academy, you need to sit down and memorize this chart. These are other alternate charts to help you kind of sit down and look at the metric system. There's another saying that you can use to help you remember the order. It doesn't cover all the way to giga or the nano, which is required by pre-AP and Academy Chemistry, so just keep that in mind if you use the chart on the left or if you're looking at the chart on the right. But just to go over that chart real quick, we have the King Henry died unusually drinking chocolate milk. And if you look at the bottom down here, it tells you you're dividing the numbers or you're multiplying the numbers by a factor of 10. That's just like moving the decimal point. So going over to this chart over here, if you're at the bench line, which is the meter, liter, gram, if you're going in the upward direction, all you're doing is moving the decimal to the left. So if I go from meters to kilometers, I'm moving my decimal 1, 2, 3 different times to the left. If I'm going from meters, let's say all the way down to millimeters, I'm moving my decimal 1, 2, 3 times to the right because I'm moving my decimal, or I'm going down those stairs. Again, pre-AP and Academy Chemistry, you need to memorize the metric conversion. You will have to show dimensional analysis, which I'll go over that in a future slide. You will not be able to do the decimal moving. You have to show your work in dimensional analysis. So if this helps you, that's fine, but make sure you follow the dimensional analysis setup as I show you in future slides. So dimensional analysis requires conversion factors, and a conversion factor is just a ratio of equivalent measurements. Hence, 1 meter is equal to 100 centimeters. And if you look at the scales around here, or the rulers, they're exactly the same. They are equivalent. So if we are converting between one unit and the next, we use these conversion factors to help us get there. More common ones that you might know, 1 hour equals 60 minutes, and 1 minute equals 60 seconds. And again, note that each number is written with a unit, hence they are a measurement. Most conversion factors that you are going to see, we are going to report them as a fraction. So they look like they're going to be in this like bracket system. I call this my bracket system. And it's just like a fraction. Treat it like a fraction, please. So if we were going to put, instead of having 1 meter is equal to 100 centimeters, as you see at the top, we can also write it as 1 meter is equal to 100 centimeters at the bottom as well. If it's within the bracket, you're good to go. That is a correct conversion factor. And then keep in mind that meters and the centimeters are a unit of distance, and you can only have similar measurements within that same bracket. So you can't put any volumetric unit on top and then a distance unit on the bottom. You cannot do that. They have to be of equivalent measurements. Okay, so I keep saying this phrase, dimensional analysis. That is just a way to analyze and solve problems using units or dimensions of measurements, and they require conversion factors in the form of fraction equivalents. So when I'm talking about the fraction, we had that 1 meter over 100 centimeters. That is a fraction, but I like to put those within this thing called a bracket because it helps me set up my dimensional analysis problem. So in the example, how many seconds are in a workday that lasts 8 hours? Well, you're probably thinking to yourself, well, I know one workday is 8 hours. I know that there are 60 minutes in every hour, And then I know that there's 60 seconds in every single minute. So if you're thinking to yourself, oh, all I have to do is multiply 8 times 60, and I get 2,8,800 seconds in one workday. Well, technically, yes, you are correct. However, there's a better way to set up these problems. That's known as dimensional analysis. And I have the steps to the right written in the box that you need to write down in your notes. So the first thing that you have to do to set up a dimensional analysis problem is write the given. The given is what is given in the problem, 8 hours. So I'm going to write 8 hours. I'm going to draw this long line. That's going to be equivalent to the line and a fraction symbol. I'm going to make my first bracket. The next thing, the step number 3, the unit that you have is going to go to the bottom. So the unit that I have, which is hours, is going to go to the bottom. The unit that I'm going to is going to go on top. So I can convert hours to minutes, and then I can plug in my equivalent measurements, where 1 hour has 60 minutes. Okay. You have an hour on top and an hour on the bottom, so they cancel out. Now I'm left with minutes. I need to get to seconds, so I'm not finished. Again, I'm going to go back and do step number 3 and 4, where the unit that I have is now going to go to the bottom, which is minutes. The unit that I am going to is going to go on top, which is going to be seconds. And within every minute, there's 60 seconds. Minutes on top, minutes on bottom, because I get to cross out those units. Now I'm left with the second, and that's the unit that I'm reporting my final answer, so now I just perform the math. If you have numbers on the top, you're going to multiply them all together. So 8 times 60 times 60 is 2,8,800 over 1 times 1, which is just 1. So you're still left with 2,8,800, but we've already learned something known as significant figures. Our given in the problem for every dimensional analysis type problem is going to tell us the amount of significant figures we need in our final answer. 8 is only one number, and it's non-zero, so it's significant. That means my final answer should be in 1 sig fig. So if I look after the 2, the 8 makes the 2 round up, so then I'm left with 3 times 10 to the 1, 2, 3, 4th power, and that is seconds. So not only do I have my answer in the correct amount of significant figures, I have my unit. Okay, what if the numbers are not always pretty? As in 60 seconds or in 1 minute, 60 minutes or in 1 hour. That's pretty simple math that we can do in our head because we know how to convert time. Well, what if those numbers are not always pretty, and what if we don't exactly know how to do that math in our head? Well, we have to use dimensional analysis. So in the book, there's a sample problem where an experiment asks each student to measure 1.84 grams of copper wire. The only copper wire available is in a spool of about 50 grams. How many students can do the experiment before it runs out? Well, we know that there's 50 grams of copper available. Each student needs 1.84 grams of copper, and what we need to know is the amount of students that are able to do this experiment without it running out. Well, I need to look at the given in the problem. In this case, my given is about 50.0 grams of copper wire. That is the given that I write down. I make my bracket system, and then I bring my grams, or the unit that I have, it needs to go down to the bottom. So grams of copper, and then I can convert grams of copper to students because I know that for every 1 student, they can obtain 1.84 grams of copper. So I am looking for students. I have the students as my last available unit because I can cross out the grams. I'm left with the unit that I'm looking for because that's what the question is asking me. So now I just perform my math, where 50 times 1, so I multiply everything across. 50 times 1 is 50 over 1.84. That comes out to be about 27.1739. There's more numbers, but that's fine. That's students. However, we need to report our answer in the amount of significant figures. Okay, so 50.0. Those zeros are both significant because they are after a non-zero number and they are to a right of a decimal. So we have 3 sig figs. So I round to my 3 numbers. The 7 makes a 1, round up to a 2. However, it's impossible to have 27.2 students. So you're just going to round to the whole number without it running out. So 27 total students can do this experiment before it runs out. So now we're going to get to the fun stuff. This is dimensional analysis within the metric system, and this is what you're mostly going to be tested on. And it all is based on the metric conversion chart that I asked you guys to memorize earlier in this lecture. So I'm just going to have it right here. It's never going to be given to you, but I want you guys to think about as if you sat down, you had these problems, and then you wrote the entire metric system based on your great King Henry chart. Okay, so we are looking for how many grams are in 750 decigrams. Okay, that's a lowercase d. Ooh, I need to fix that. That should be lowercase, and then that should be lowercase as well. So our decigram, we're given 750 decigrams, and we need to convert to grams. Okay, so following the same steps as I have been, we need to write down our given. So I have 750 decigrams. I draw my dimensional analysis bracket. Decigrams, the unit that I have, needs to go to the bottom. I do that so I can cancel out those units. I'm converting decigrams to grams because that's what the problem says. How many grams are in this many decigrams? So the unit that I have goes straight down to the bottom. The unit that I'm going to goes up on the top. Now I need to look at my metric system chart. This is where it's going to get confusing. I want everybody to look up at the top screen. The bigger unit will always have the number 1. So that's the number 1 in the bracket system. That is because I do not like working with negative exponents. So to eliminate the negative exponent situation, we always put 1 with the bigger unit. How do we know what the bigger unit is? You just go from top to bottom. Whichever unit that you run into first, that is the bigger unit. So if you start from the top and you go down, will you run into grams first or will you run into decigrams first? And if you go down, you run into the gram first. It's right above the decigrams. So gram is the bigger unit. It'll always get 1. And now we have to think about, well, what goes in the decigram? A power of 10 to the exponent that we have to figure out is going to go into the decigram bracket. So we have to figure out what exponent goes with the number 10. Because again, don't forget, all these factors are based on powers of 10. Well, gram is my base. Decigram is 1 away from the baseline. So the power that goes into this bracket is going to be an exponent of 1. So then my units that I have on both the top and the bottom are going to cancel out. Now I multiply the numbers on the top. So 750 times 1 is 750. All over 10 to the first power is still 10. So it's just 750 divided by 10. That equals 75. So there are 75 grams in 750 decigrams. I also have to go back and double check to make sure I'm in the correct amount of significant figures. And just to review that real quick, in 750, that 0 is non-significant because there's no purposely put decimal, so there's 2 sig figs. And my final answer has 2 significant figures because the 7 and the 5 are significant, so my answer will get all points. Going down to the next problem, I'm looking for how many centimeters are in 225 kilometers. Well, I need to write my given down where I have 225 kilometers. And I need to figure out how many centimeters are in 225 kilometers. So I'm converting from a kilometer all the way down to a centimeter down to here. So this C. I'm going from this K to that little C down there. So again, I draw my bracket system. The unit that I have goes down to the bottom. The unit that I'm going to goes on the top. Again, that's an error. It should be a little c, so make sure you put little c with an M. Now I need to figure out which one is the bigger unit. Well, if I go from top down to the bottom, I run into the kilometer first. So that makes kilometer the bigger unit, and as always, the bigger unit will always receive the number 1 to eliminate the negative exponents. Okay, so now I need to figure out what exponent goes with my base of 10. Okay, so in the previous problem, we said that the decigram was 1 power away from the base. But now I'm going from 10 to the third all the way down to 10 to the second. So you need to think about the metric system being a number line and that this baseline is just your 0. So if I go from 3, this power of 3, to 0, that's 3. And then if I go from the base down to the 2, that makes it 2. So I have 3 plus 2, that would make my power of 5. It's like a number line. Okay, so I want everybody to realize if you're on the same side of that number line, you're going to subtract those powers. But if you're on the opposite sides, going from one side to the other across this base, you're going to add those exponents because you're counting the distance away from each other in the form of the power. So going down from 3 to 0, again, that's 3. And then this 0 to 2, that's 2. So the total would be 3 plus 2, and that's where I get my exponent of a 5 from. So I'm going to erase this so I can write my answer. Okay, so then I am ready to do some math. All right, so then I have 225, multiply everything across on the top, so 225 times 10 to the 5th power. I get a very large number, and that's never good to report it that way. It's reported as 225 with 5 zeros. Do we ever want to see a number like this? No. So we need to use scientific notation. In my given, I have 3 sig figs because of the non-zeros. So I just report my answer in 3 significant figures. I can use scientific notation where I have 2.25 times 10 to the 1, 2, 3, 4, 5, 6, 7 power, and then I need to write my unit centimeters because the kilometers cancel out. So there are 2.25 times 10 to the 7th centimeters in 225 kilometers. All right, so now we're going to get to more advanced dimensional analysis where we're going to convert between 2 different units. So it might require multiple brackets. Only convert similar units within each bracket. That means within one bracket, if we have volume in liters, we can only use volume units. If we're also converting between different mass units, you can only have mass equivalents within one bracket. You cannot have anything going from a mass unit to a volume unit, for example. That can't happen at all whatsoever. So if we're using this problem, if Susie is driving 85 kilometers per minute and the speed limit is 65 miles per hour, is she speeding? Well, the first thing that you always need to do is write your given down, which is 85 kilometers per minute. I'm going to make one bracket at a time. The unit that I have, kilometers, is going to go down to the bottom. The unit that I want to go to is the mile, because it's asking me if she's speeding, so I need to figure out my miles per hour. You have an equivalence given here. This you won't have to memorize. The only thing that you do have to memorize is the metric system, so make sure you go back and learn that. And so for every 1 mile, there is 1.609 kilometers. Kilometers on top, kilometers on the bottom, cancel out, and now I'm left with miles per minute. Well, I still need to get to hours, so now I'm looking at my minutes. Well, Because kilometers was on top here and kilometers was on bottom here, I was able to cancel them out. The fact that minutes is on bottom, I need to bring minutes to the top so I can cancel it out. So converting minutes to hours, I know that for every 1 hour, there's 60 minutes. So now I can cancel out my minutes. I'm left with miles per hour, so now I can do my math. Well, 85 times 1 times 60, so I multiply everything on top. I get 3169.67 and a lot more numbers over, we have 1 minute times 1.609 times 1, which is 1.609, dividing oops, I'm sorry guys, I went ahead of myself and I got the 3.169 earlier. The top actually multiplies to 5,100, and then on the top 5,100 divided by the 1.69 if you look up at the top. So we have 5,100 on the top divided by our 1.609. That actually led to the 169.67 unit. I apologize if that's confusing. I can go over this problem on Monday if this kind of confuses you guys. However, we just have to report it in the correct amount of significant figures. I'm starting with 2 sig figs, 85, so I can use scientific notation to round my number. 3.2 times 10 to the 123, and that's in miles per hour. Obviously, she's speeding because this number is outrageous. I don't think anybody would be driving this much, but that's the fun thing about making up numbers. Alright, so it's time to practice. So what I want you to do right now is to press pause, try to work these practice problems, and then come back to them once you think you've gotten the answer, just to double check. But if you think you got it right, I'm going to go ahead and work these problems. But first I need to write my conversion chart, which is my great man, King Henry, danced merrily, lazily, gracefully, down center Main, under Narnia. Okay, so then we got to write in our powers of 10. So we have our baseline of 0. I'm only going to write the exponents. 1, 2, 3, 6, 9. And then you go down to the bottom, -1, -2, -3, -6, -9. You don't have to include the negative numbers because, again, we put 1 with the bigger unit. So it takes away the fact that we're not working with negative exponents. But I just didn't want to confuse you guys. So if we're converting 0.0044 kilometers to meters, again, you always write your given, which would be 0.0044 kilometers. Now I'm going to go to meters. The unit that you have goes straight down to the bottom. The unit that you're going to is going to go on top. Going from the top down to the bottom, you have to figure out which one's your bigger unit, which is kilometers, because you run into kilometers before you get to meters. So the 1 always goes with a bigger unit. Now we have to look at the exponent that goes with the base of 10. Going from kilometers at a 3 to our baseline of 0, if we're on the same side, we subtract. So at 3 minus 0, we get a power of 3. So in our calculator, we will take 0.0044 times 10 to the third power, and then we end up with 4.4 meters. Okay. Well, I didn't exactly put a number with the first milligram, so I'm just going to go ahead and convert 565 milligrams to megagrams. So I'm going to erase the top here and kind of get you started on the second problem. Okay, so let's write our given. I have 565 milligrams, that's little m, and I'm going to go to megagrams, that's the big M. So I am at little m down here, and I need to go to the big M at the top. So the unit that you have always goes down to the bottom, and the unit that you want to go to is at the top, and I wrote that really large. Okay, so which one's the bigger unit? Not the size that I wrote big, but going down from the top to bottom, you'll hit megagrams before you hit milligrams. So the 1 always goes with the bigger unit. Now I need to figure out what what exponent goes with my 10. So I'm on the opposite sides of the baseline, so I need to add those exponents. Okay, so your megagram has a power of 6, your milligram has a power of 3, so 6 here plus the 3 down here, you get a total of 10 to the 9th power. And if you want to look at it, 6 to 0 is 6, this 0 to this 3 is 3, so the total distance would be a power of 9. So in your calculator, 565 times 1, that's 565, all over 10 to the 9th. So putting that into your calculator, you end up with 5.5 times 10 to the negative 8th megagrams. Okay, so then I'm going to go ahead and erase this so I can do the bottom one because I'm going to need a little bit more room. And I apologize if any of the metric system is hard to see because I've been writing all over it. Alright, I'll try to use a different pen when I use that. Alright, so the third problem, convert 25 grams per liter, and you're converting that to kilograms per deciliter. Hey, don't forget that you can only convert between one type of measurement. So I'm going to go ahead and start with grams, and I'm going to convert to kilograms. Okay. So your kilogram is, again, it's on top. It has this 3. I'm going to use yellow for this problem. And then your grams, this is the baseline here. So obviously the K is on top. K is the larger unit, so it's going to get the number 1. Then how far away is it from kilogram to gram? You're on the same side, so you can subtract 3 minus 0. So you have a power of 10 to the 3rd. Because gram is on top, gram is on bottom, they cancel out. Then you're left with kilograms. Now I can convert liters to my deciliters. Because liters is on the bottom, you have to bring that up to the top so you can cancel out the unit. And then I'm going to convert to the deciliters. That's the lowercase d. So going from liters, which is at your base, to the deciliters, the liters is on top because you hit that first as you go down the metric system. So liters will always get the number 1. Oops, wrote the wrong color. 1. And how far away is it from the liter? Well, you have a base of 10 always. 0 at the base to that 1 is a power of 1. Okay, so liters on top and liters on the bottom cancel out. Now you just perform your math. On the top, you have 25 times 1 times 1, which is just 25. Divide that by 10 to the 3rd times 10 to the 1. Remember, whenever you multiply bases of 10 or similar bases, you add the exponents. So you should have 25 divided by 10 to the 4th power. 10 to the 4th, 55 divided by 10 to the 4th, you should get 0.0055. We don't like to write numbers like this, so I would go ahead and use scientific notation. That way you can also make sure it's in the correct amount of sig figs. So I'm going to write it at the top. You should get 5.5 times 10 to the 1, 2, 3, negative 3rd, and that is in kilograms per deciliter. You can just box that there. So please go back and check your answers and see if you got them right, and if not, please try again and see if you can get the same answer that I just did. Okay, so have you accomplished the objectives? If you have not, please go back and restart this lecture. This lecture is probably going to be the most important lecture of the year. We convert all year long, and you need to be able to convert between the different types of metric units. Please go back and memorize your metric conversion chart. That's the King Henry chart. That will be one of the most important things that you do all year long. And if you can do this now and use dimensional analysis, I promise it'll make your life easier when it comes to future topics. So go back, do those practice problems. Whenever I see you guys the next time in class, we'll be able to work more problems, additional problems. So hopefully we can get this underneath our belt and move on. Thanks.